kimberlitic mantle and some features of kimberlite and diamond formation and the history, geological history of the platform. Simple scheme of cross-section of lithosphere of Siberian platform for mid-Paleozoic time. Why for mid-Paleozoic time? Because if we will take this cross-section in Mesozoic time, it will be significantly different. Okay. Thickness about 250 kilometers. Here is crust, spinel dolsolite, garnet spinel dolsolite. It's all of these depleted presentizing, of course. It's graphite diamond transition zone. Depleted, extremely depleted hardwood and granites. Some of them are diamondiferous, and some are personites in this area. And here we have secondary enriched peridotite. It's a zone of interaction of conducting asthenosphere and peridotite, depleted peridotite of lithosphere. It's secondary enrichment is here. Diamonds are in this cross section are situated, diamond microspherules are situated in this area. Okay. A little bit about garnetization reaction in Siberian upper mantle. It beginning of this reaction depends from this ratio. It's correlates with depletion, level of depletion of peridotites, and if you have this ratio chromium to chromium plus alumina, say 0, this reaction will start here and finish in here in this spot. But if you have, say, 60, it will start here at much higher pressures and finish right here. And also, it depends from temperature. If this is temperature, it takes higher pressure to start and to finish this reaction. Okay. Using this feature of this reaction and also nickel chromium thermobarometer by Ryan and Griffin, we'll try to estimate thickness and heat flow for lithospheric mantle for Siberian platform for Paleozoic time, mid-Paleozoic time, and Mesozoic time. For Siberian platform, we have 3 main cycles of kimberlitic magmatism activity. It's upper Devonian, about 350 to 370 million years, and Triassic about 230 to 235 million years, and upper Jurassic from 170 till 145 million years. And this Mesozoic kimberlites they have in this area, and in the same area they have also Paleozoic, mid-Paleozoic kimberlites. So they can compare some xenogenic material from Paleozoic kimberlites and Mesozoic kimberlites as well. And the same they have in this area and southwest of Siberian platform, as Tunguska Cineclass with full basalts right here. And here they have northeastern part of Siberian platform. It's Olenek up left, and they have here also many hundred of kimberlites of Mesozoic age and a few bodies of mid-Paleozoic age, and so on. If you will see on this plot chromium to calcium side for pirates, for mid-Paleozoic kimberlites, we have such picture. Amount of chromium more than 12% up to 13%, and all the lithic garnets are related with this trend. Perhaps from Mesozoic kimberlites, we see a limit is 7% of chromium oxide, and they have absence of harsh-orgitic, low calcium, high chromium garnets at all, no diamonds in here, and this trend, look on this, and it's different from this, it's much higher, and it crosses this alternative trend, it's so-called peroxenic trend, and the same for this area. Okay, using nickel chromium thermobarometer, they have calculated thickness and heat flow for different areas of Siberian platform. The main is that for mid-Paleozoic time, they have pretty thick and cold lithosphere. Heat flow was around 36-37 milliwatts per square meter per second, and thickness of lithosphere was about 230 to 140 kilometers. And for Mesozoic time, they have heat flow about 41-42 milliwatts per square meters per second, and thickness of lithosphere was about 150, not more than 150 kilometers. So they have significant decrease of thickness, about not less than 80 kilometers decrease of thickness. It is shown here. Okay. Different of thickness first, absence of diamonds, because this they have not this depleted, extremely depleted peridotite, diamond-bearing depleted peridotite for Mesozoic time, and significant, maybe 10 times increase of presence of peroxenites. So it related with significant basification of lithosphere as a result of influence of Siberian superclone related with border of Permian and Triassic period at about 250 million years ago it was happening. Okay, now to diamonds. Back to peridotites. Depleted, extremely depleted peridotites, all the cases, chromium-rich magnesium garnet, all of it, and statite. This introducing of carbonatic melt, it increase of calcium, first produced increase of calcium in garnet, up to here. Here they have it's start decarbonation, and statite will start to transform into CPX, like this. And then statite will be finished, statite phase will be finished. They have increase of calcium in garnet. Garnet transition with CPX. Verlitic parashemicis can go up to here, and after that, when we have no capacity of garnet for calcium, we have carbonation of peridotites. It's in paper of Siberian, it was shown this process of carbonation. You can see this newly formed CPX, like here, some bubbles of CO2, and this reaction is right here. And the same was shown in a paper of Joe Boyd and myself in 1997, also for keratites of from Udachny Empire. Okay. So, introduce of carbonated melts changed some rare earth pattern for garnet. We have some stuff like this. We have elevation of Alantans group, sometimes Brazil group with increase of this metasomatic treatment in garnet. Okay. And this sign type of rare earth distribution is typical for from four garnets from rich low calx and high magnesium pyrops for depleted keratites of deepest levels of Siberian lithosphere. These dunites are situated right here. Okay. And if you will see on this pressure and temperature diagram, we have this area. And oxygen fugacity, you can see that it's changed significantly for this. And some of these keratites are diamondiferous. Maybe for Udachny, if we have calculated amounts of diamond keratites for Udachny pipe, about 9–10% of depleted Habsburg contain diamonds. And with increase of this, you can see that our area is like here. Okay, now diamond being Habsburg is from Udachny by here have demonstrated that all the diamonds from his example of Edwardite are related with some grains of cracks. The same for the diamond-differous keratites. You have this weathered crack and diamond right here. The same here. Not inside of olivine grain, but related to scrap. But the same here. It's extremely fresh. Diamond and also crab. It's very, very fresh. Generally, it's of diamond-differous tonight. But also we can see some cracks and some metasomatic agent penetrates and forms these diamonds. They have only just one a single find of olivine megacrist in Udachny without any cracks, with small, tiny inclusion of diamonds. It can be related with the earliest diamond formation in the lithosphere Siberian platform, but not only in Siberian, but for Siberian platform, because together with the diamond in this grain crystal of olivine, we have two inclusions of sulfide, and it was possible to date them, and they attained their age 3.4 billion years. It can be initial stage of diamond formation related with generation of diamonds from carbonate during high temperature silicate melts. Okay. Now to short elements. I told you when we look cross section of lithosphere of Siberian platform. I told you about the secondary enriched peridotite. It's so-called shear peridotite or deformed peridotite. Structure, texture of them, they can see in here. And depth, you have the deepest, and temperature are highest, up to 1400 degrees. And this generally we can see some inclusions of carbonate melt inclusions, and this all the rings from these rocks right here, Katayama and Alex Golovin. This aragonite, as first high pressure phase. And another, it's traces of some signs of carbonatic melt, but another metasomatic agent is basaltic melts. And here we have some example of rim of initially it was dunite garnet with very low calcium, less than 2%, and high chromium, more than 11% of chromium oxide, and high magnesium. And here it's calcium. We have increase of calcium from very homogeneous core, subcalcium homogeneous core, and in this situation, in association of such garnet, pyroxene CDX is prohibited. But here we can see a lot of them. All these black or white as CDX. Okay. And another example. You see also homogeneous, practically homogeneous core of subcalcium high chromium garnet, increase of calcium, and some maximum amount right here, and then decrease again. Okay. Some another. We have a low iron in the and increase of iron in rig. Titanium, also low titanium, practically absence, less than maybe 0.05 of less than 0.1% of titanium in the core, and up to 1.5% in ring of titanium. Chromium decrease of chromium, and I will show you such chromium stable and high in core, and decrease less than 1%. Increase of calcium, yttrium, strontium, also we have the same increase for titanium and zirconium. Okay. Red earth elements. Core is typical sine-type red earth buffers, like for normal. Transport guys said do not some of them I told you about that can be diamondiferous, and core it's ring. You can see like this. It's normal. Some increase of light lanthanum cerebral roof can be related with interaction with kimberlitic melt. And to calculate the composition. First, garnet which was crystallized from Siberian fluid basalt composition. And second, this one, triangle, red triangles. It's mixture from core and this calculated garnet which must be crystallized from tolerific basalt. You see, it's very corresponding. real composition. Okay. And now back to chromium and calcium. This increase of calcium is a carbonacetic type of metasomatic treatment. Increase of calcium. And then here we have some pyroxene and decarbonation and decrease in new form of garnet, this decrease of chromium. And what iron? Core is very low iron, about 7% of here. And rim up to 12%. This decrease of chromium. And here we have some real garnets from garnet peroxenides from обнаженной, мезозоик, обнаженная pipe, mid pipe, mid paleozoic, and удачная also mid paleozoic pipe. You see this trend across this lapsolitic trend like this, goes like this. And now what we have for ICAL pipe, it's very diamond-rich pipe, and we have a lot of these low calcium, subcalcium, and high chromium garnets, and a lot of diamonds as well. Ivushka pipe, it's low, not too much diamonds, but diamonds in first pipe of mid-Paleozoic age and situated exactly in this place like Musa pipe is Upper Jurassic pipe. Absolutely different, you see, trend. No absence of these garnets, absence of diamonds. This feature can be used for diamond exploration. This area is low Paleozoic cumulative field. It's Lena River right here, as ocean is here. Well, different areas. It's Ivushka pipe again, diamondiferous. This line divide diamond garnets formed in diamond, definitely diamond stability field. It's a graphite stability field, and this area, Olahan Intech, about we have in some granulates secondary collectors, we have diamonds and such pyrops. You see very high amount of these diamond pyrops formed in diamond stability field. And in these granulates, we have very high amount of diamonds. It's practically Asian placer for diamonds in this one. It means that in this area it's possible to find primary source which will be such rich in diamonds like, say, Udachная pipe, the biggest diamond mine in Siberia. And another area, it looks like that the deals with pyrops originated from Mesozoics, such Musa pipe, but it is not necessary to continue exploration in this area. No any evidence, no signs of presence of diamond bearing high-grade kimberlites. And here it's some. So it's possible to continue here at Kuchumbier River Basin. We have some good hopes to find some diamond interest. Okay. Back to shear peridotite. You see shear peridotite from Udachная pipe. It's green squares. And it's depleted Habsburg acid. Here are primitive mantle. Here practically full range. Evolution from primitive mantle, it goes like this. Then, in secondary enrichment by carbonacetic metasomatic treatment, it's mixing this kimberlite right here, this proto-kimberlite here, 5%, 10%, and they have a real composition in here and here. And then secondary enrichment by basaltic melt. Also, they have practically a full range from here up to here. Okay. That's possible to do. Well, I talked about the carbonation of peridotite. It's happened when we finish capacity of garnet to contaminate to use calcium, and then we have carbonation of peridotite, and sometimes it's possible to find very interesting primary kimberlite carbonatite assemblies like it was found in Canada. It's like lake dye system. It's very high grade kimberlites, very interesting diamonds, very expensive diamonds. It's practically 2 times price for these diamonds higher than for normal kimberlites, say like for Udashna or and primary origin of carbonatites is shown by distribution of earth, because in case of liquidation, this heavy lantanoid ytterbium group, ytterbium group must go into basaltic melt, and in case of melting of carbonate peridotite in case of extremely deep lithosphere, primary melt will contain this material carbon dioxide. It's shown in here. We have significantly higher amount of these heavy lantanoids in carbonatite. Okay, it's normal kimberlites. Kimberlites of group 2 produced by partial melting of prepared by metasomatic treatment by carbonatic agents and carbonatic and basaltic agents. But these unusual kimberlites, you see, like slightly in a very deep lithosphere by partial melting of slightly carbonated depleted lercelites, peridotite. So, and extremely deep, extremely high thickness of lithosphere beneath the plane is shown by composition of carbons. You see, if they will take such amount of pipes from nearby, for example, or from South African premier mine, limitation for chromoxide is about 12%, but we have here a much higher amount, up to 18%. Remember this scheme of granitization ratio. To obtain such amount of chromium, it takes much higher pressure. And some support of this is they have from diamonds again. They have some inclusions in diamonds of subcalcium high chromium pyrites. This excess of silica in model up to 3.17. It is pressured about 110 kilobars to reach such amount of excess of silica. So it corresponds to depths about not less than 300 kilometers. It's a very interesting diamonds. Isotopic composition, it's looks like they are crystallized from maybe from methane, because they have analyzed about 3 tenths of diamonds, and isotopic composition is between 3 and 4 per bill of C13. It's much heavier if compared with normal diamonds. Another, these deep-seated diamonds, you see, is interesting. They have inside some fragments of diamonds, another diamonds. You see, it's fragment. You see, it was broken octahedral diamond, and here as well. It's a question: how is possible to reach such pressure? Stress pressure to enough to crack this diamond. You see, it's I told that it's about 300 kilometers depth. Okay. Now a little bit to fluids. It's melted of methane. It's Sergei Lofanov in Nature Communication obtained such high alkanes at depths corresponding to about 40 GPa. And here they have some heavy hydrocarbons included in nature of diamonds. You see, it's fluid inclusion of Siberian diamonds. They have such up to, you see, C15. Okay, two conclusions. Structure and composition of Siberian platform were changed several times in geological history, and the most significant event of this kind of changes was related with influence of Siberian superclume and the periods. Diamonds can be formed in low mantle, sublithospheric upper mantle, but the majority of diamonds transported by kimberlites to the Earth's surface were formed in the lithospheric mantle roots. Origin was significant part of lithospheric U-type diamonds related with initial stage or the carbonacetic and metasomatic metasomatism of highly reduced depleted pyramidites or the cartonic roots. And interaction of carbonated wells is H2O period reduced depleted pyramidites produce wide range of heavy hydrocarbon compounds, 16 or even heavier. And these conclusions generate a very important problem of estimation of possible amounts of oil and gas on the mantle origin. Thank you.
Some questions? Yes. Okay.
I think you showed us that the main effect on Siberian lithosphere was between second and third stages of kimberlites, but that is well after Siberian flood vessels stage. So how do you explain this delayed influence of Siberian superclume on Siberian lithosphere?
Okay. Actually, they have, I showed you some xenoliths of Harshburgite from Udachная pipe. Udachная pipe is mid-Paleozoic, and it was visible that they have some transformation of Harshburgite into enriched lepsolite. You see, there's a lot of CPX and so. That was happening in mid-Paleozoic time. But this, if we will compare distribution of peroxenitic and pegmatitic rocks in cross-section of Siberian lithosphere in Paleozoic time, we have this peroxenitic material about 3.54% only. But if we will deal with Mesozoic kimberlites, this amount will increase sometimes up to 70–80% of parasitic material in cross section of kimberlites. And also, if we will try to estimate thickness for the same area in northeast of Siberian platform, in mid-Paleozoic time, for example, for Ivushka pipe or for garnets, we will obtain from secondary collectors of Carboniferous age, mid-Paleozoic age. It will be about 230 kilometers. But if you will take the same area, absolutely geographically, absolutely the same area, for Mesozoic time, we will obtain just 150 maximum 150 kilometers. It's difference in thickness 80 kilometers.
So why?
Okay. Why? Because when this superbloom reach these roots of lithosphere, it start to interact with this metasomatic treatment of these roots will, some of them does contain some, I showed you, some secondary enriched material. In case of low heat flow, it's not enough temperature at this depth to start to initiate partial melting. It's secondary, it needs some additional heat. So, and looks like this superbloom produce this additional energy, heat energy, plus some volatiles, of course. Yes, it will be enough to obtain maybe 10, several percent, maybe less than 10% of melting, but it's enough that this amount of melt is possible to make viscosity of this material much higher, and it can be involved in convection, you know.
Next, Eric.
You should done in cracks, and the cracks narrower than done in size. How do you explain it?
Yeah, I think that here also showed some diamonds with crack. Diamond during its growth can, because it's crystallization energy of diamonds, it's possible for diamonds to make bigger volume first, and second. When we deal with such example, sorry.
Here.
It's not very clear. You see, not very big diamonds. You see, crack enough big for that. Here also, and here, it's comparable size.
No, it's certainly the crack narrow at the dark. Do you think that it's possible that the seed of the diamond produced from the fluid and then the grew in the cell?
Of course,
And
because you see this fluid contains carbon, because this surrounding
and I just realized the suggestion that the production of seed of fluid was by cavitation mechanics.
not cavitation, of course.
I thought.
because you know it's PT conditions of this formation for this rock. About 50-55 kilobars of temperature, about 1,000 degrees, you see, and looks like structure of the diamonds is very stable. Some of the diamonds, they have some tiny contributions of such minerals like surrounding rocks, you see. It means some, these growth is relatively stable conditions, not like conditions.
Growth, yes. Growth.
But
I'm talking about seed.
seed can be, I don't know, but why? In Institute of Experimental Mineralogy, it's a laboratory of Yuri Litvin and Polyanov. They say we have such in conditions of diamond stability field experiments. It's going nucleations of diamonds, no problem. No problem without any movement of the liquid.
In which concentration of carbon?
You see different concentration in, well, when we have this metal, no problem. You see we have graphite and saturation of metal, but speaking about this, well, they have some crystallization from carbonatic milk, yes. Also, when in some silicate carbonatic wells, we have, say, 20-25%. 20-25% of
we have in the metal 0.001% of carbon. How would you explain the nucleation in this?
I have, okay, we have some carbonatic fluids included in all of them. You see? Yes, we have.
Maybe you're right in this particular case.
I apologize because we have.
People like
Yeah. First of all, thank you very much. And now, coffee break.